How's it going? This is Mike coming back at you here with another video on number theory. In the previous video, we saw several example problems as to how do we use the Euclidean algorithm to find the GCD of two numbers. In this video, we are going to learn about a process related to the Euclidean algorithm. In fact, it's very related to it. And we're going to use this new process to find out some handy pieces of information that we referenced earlier on in this chapter. This method that we're going to look at and we're going to see several sample problems with. This is also going to help us for our next section when we solve a particular type of equation. So earlier on in this chapter, we saw a theorem that said that if you have two integers a and b, not both of them 0, then we can find integers x and y such that the GCD of a and b is equal to ax plus by. And this theorem just said that we have these integers x and y. It didn't tell us how we find them. Well, now we come to the process that shows us how do we find these things. And how do we actually find these integers x and y? We're going to reverse engineer the Euclidean algorithm. Now, as you'll see when we go through this, we're going to write things in kind of odd ways, but we do that purposely. You're going to see that we're not going to multiply things. We're going to purposely leave things in a particular form. So pay very close attention to that. This may be a little bit odd, but once you get to the end of this video and you see the few sample problems that we do, it should begin to make sense why we're doing what it is that we're doing. So in the notes, we found the GCD of 12,726 and 3,024. We want to find the integers x and y such that 12,726x plus 3,024y is equal to the GCD of 12,726 and 3,024. And if you look back in the notes, when we did the Euclidean algorithm to figure out what the GCD is, we found that the GCD was 126, and these were the set of 4 steps that we used. So here's what we're going to do with the reversal or the reverse engineering of the Euclidean algorithm. What you'll do to start off is look at every row except the final row. So every row that has a non-zero remainder. What you're going to do for each of these rows is you're going to solve for the remainder in the use of the division algorithm for that particular row. So for this first row here, I'm going to solve for the 630. I'm going to say 630. Now, we just have 12,726. I'm going to specify that I have one 12,726. So 1 times 12,726, and then I have minus 4 times 3,024. And it may seem like I'm writing this in a weird way, but you'll see why I'm writing this in this particular way as we go through these problems. We're going to do the same thing for the next row. The remainder in this row is the 504, so I'm going to solve for the 504. So 504 is equal to 1 times 3,024 minus 4 times 630. And we do the same thing for the final row. 126 is 1 times 630 minus 1 times 504, and we have all of these remainders solved for over here. And as we reverse engineer the Euclidean algorithm, we're going to see that these guys will be very important. These are the pieces that we're using to find these whole numbers x and y. So it's very important that you keep those out somewhere so that you can easily refer back to these guys. And I'll be flipping back and forth between these slides quite a bit. So I'm going to start with my last row, that guy there, and then we'll see as we go through this problem. I'm going to use the next row up, combine things, simplify, then use the next row up, combine things, simplify, all that kind of good stuff. But you always start at this point, you always start with the last row. So 126 is 1 times 630 minus 1 times 504. Okay, looking back at our three equations here that we found here, I have a 504 here. So I can make the substitution for 504 in that first line on my next slide. So I'm going to take that 1 times 3024 minus 4 times 630, and I'm going to substitute it in for this 504. And when I do that, we see we have the 1 times 630. Those are matching up. And then I have the minus 1 times, and this was our 504. Now, how do we get from the left-hand side of this to the right-hand side? I'm going to multiply this negative 1 into each of the numbers out front here. So I have a negative 1 times a 1 times a 3024, and I have a negative 1 times a negative 4 times a 630. Well, I have 1 630 and then plus 4 630s. So what I actually have are 5 630s. And then I had the minus 1 times the 1 times the 3024. So I have negative 1 3024s. So that's how we go from the left-hand side of this line to the right-hand side of this line. Note that I'm only taking this number here, and I'm only multiplying it into the number out front. I'm only multiplying it into the 1 and this minus 4 here. You want to leave the other numbers as they are. You want to leave the 630 and the 3024 as they are, because we'll be making substitutions for the 630, and we're going to see that 3024 is one of the final numbers we want to see when we're all done with our work. So now we're at this stage. We're at 5 times 630 minus 1 times 3024. All right, I'm going to go back to my slide here where we found where we solved for each of our three remainders. Here I had a 630. Well, here I have a 630 in times of 12,726 and 3,024. So I'm going to make this substitution. This here is going to go in for my 630. When I do that, we see that this is exactly what 630 was, and then everything else is the same. I still have the 5 out front minus the 1 times the 3024. Once again, I'm going to multiply the 5 into each of the numbers out front, and only the numbers out front here. I'm not going to multiply it into the 12,726 or the 3024. I have then 5 12,726s, and then I have minus 20 3,024s, and then I have minus another 1 3,024. Or I have 5 12,726s, and I have negative 21 or minus 21 3,024s. So this right here is equal to what my GCD was. This is equal to that 126. The question said, find the integers x and y such that the GCD of these two numbers, 12,726 and 3,024, is equal to 12,726x plus 3,024y. Well, 12,726 times x plus 3,024 times y is equal to 126, which was my GCD. So these coefficients that we have here, those guys are the integers x and y that give me my GCD. So we have our answer. We have our x and y values. X is 5 and y is minus 21. So that may seem a little bit odd at first, why we wrote things how we did, but we still have a couple more samples here, so we'll go through those. We'll see how these things make sense. Next one, working with some slightly smaller numbers. Again, find the integers x and y such that the GCD of 6,603 and 1,136 is equal to 6,603x plus 1,136y. First thing we have to do is determine what is the GCD. To do that, we use the regular Euclidean algorithm, aka repeated use of the division algorithm. When you do that, I'll let you verify this on your own, but you find that the GCD of these two numbers is 71, because that is the last non-zero remainder that we have here. So we know what our GCD is. Now we need to find the integers x and y such that 603x plus 1136y is equal to that 71. Next step, take each of your lines that has a non-zero remainder, solve for that remainder. 923 is 1 times 6603 minus 5 times 1136. 213 is 1 times 1136 minus 1 times 923. And 71 is equal to 1 923 minus 4 times 213. Just subtracting a term over to the left side in each of those lines. These are the guys that we're going to use. So keep these guys in an easily accessible place. We always start with our bottommost row in this column. So we're starting with the 71 equals 1 times 923 minus 4 times 213. Again, going back to our previous slide, we have 213 in terms of larger numbers, specifically in terms of 1,136 and 923. So I'm going to make this substitution in for the 213 in this line here. Again, the 1 times 923, just copying that down, minus 4 times, and now this is where the substitution for the 213 comes in. I'm going to take this number out front. I'm going to multiply it into the first number in each of these products, not the second number. Negative 4 times 1 gives me negative 4 1,136s. And then negative 4 times negative 1 gets me a positive 4 923s. I have 1 923 plus the 4 923s to give me 5 923s. And then we have the negative 4 1,136s. So now we have our GCD in terms of 923 and 1,136. We're very, very close. We want our GCD in terms of 1,136 and 6,603. So I'll go back to our remainders here. We have 923 in terms of 6,603 and 1,136. So I'm going to make the substitution here in for the 923. When you do that, 5 times, there's our substitution for 923, and then the rest carries down as the same. Multiply the 5 into the first number here. I have 5 6,603s, and then here I have minus 25 1,136s. And then carrying down, minus 4 more 1,136s. Well, if I have negative 25 1,136s and I subtract 4 more, I have negative 29 1,136s, and I still have my 5 6,603s. You could pull out your calculator now at this point and do 5 times 6,603, do 29 times 1,136, and take the difference, and you would indeed come up with 71. So there is always that check to make sure that your math is valid and you didn't goof off somewhere. We wanted the integers x and y such that our GCD was 6603x plus 1136y. 6603 times x plus 1136 times y. So in this case, our x and y values, x is 5 once again, and this time y is equal to 29. So this was a very, very similar sample problem to the first one. Any problem that you'll see on a homework or quiz or test is going to be about this long. Maybe there'll be one more step involved here, maybe, but something like this is not too bad. It's not too time consuming. So these were a couple samples here. I'm going to let you guys work on the next example on your own. So if you need to rewind, take a look back at these, try to make sense of this, then pause the video now, do that, and then press play once you think you're feeling good. The problem that I want you to work on your own, same kind of thing. Find the integers x and y such that the GCD of 1,507 and 627 is equal to 1,507x plus 627y. So do what we did in the two previous problems to figure out x and y. First, you need to find the GCD using the Euclidean algorithm. Then you need to solve for each. Non-zero remainder. Then you sort of work your way backwards through the division or through the Euclidean algorithm. My apologies. Substituting those remainders back in until you get 1,507 times some number plus 627 times some number. Once you've found those numbers, those are your x and y values. So press pause here. Try to solve this problem on your own. Once you're done and you think you have it, press play, and we'll see if you are correct. All right, guys, let's see if you came up with the correct values for x and y. First thing we had to do is find the GCD and then solve for each non-zero remainder. On the left is solving for the GCD, which hopefully you found was 11. Another fairly short use of the Euclidean algorithm here. In the right-hand column, I just solved for each of our non-zero remainders. So these are the guys here that we're going to use in our next slide. You always start with the bottommost row that we have in this right-hand column. So 11 is 1 times 253 minus 2 times 121. I have 121 in terms of 253 and 627. So I'm going to make that substitution to give us this left-hand side here of the second line. Multiply the -2 into each of the numbers out front, and then combine like things. I have 5 253s, because the -2 times the -2 gets me a +4, plus the 1 I had out front. And then I have -2 627s from the -2 times the 1. All right. I have 253 in terms of 1,507 and 627. So I'm going to make that substitution. And when you do that, there's your substitution happening there. Multiply the 5 into each of the numbers out front. Combine like terms. You have 5 1,507s and then -12 627s. So 1507 times x minus or plus 627 times -12, or your y. So we have our x and y values. X is 5 and y is -12. It's not necessarily always going to be the case that x is equal to 5. This is just what we see from these few sample problems that we had. But again, focus on the method that we are using here. We are doing the Euclidean algorithm to find the GCD. Then we are taking each of the rows in that Euclidean algorithm that have a non-zero remainder. We're going to solve for each non-zero remainder. We then start with our bottom row there on in that right-hand column, and then we use the next line up, substitute in, combine like terms, group things, then use the next line up, substitute in, combine / regroup like things, and you would keep doing that until you've used all of your rows in that right-hand column. You then identify what are the smaller numbers, typically, in most cases, the smaller numbers in front of those large numbers. And those are the x and y values that you are looking for. Just a couple things I want to wrap up with. For any integer k that's not 0, if you're taking the GCD of k times a, and k times b, that's equal to the absolute value of k times the GCD of A and B. So just as a quick sample here, say we had the GCD of 1760 and 240 here. Well, each of these guys contains a clear common factor of 10. So the GCD of 1760 and 240 is 10 times the GCD of 176, my apologies, and 24. We could then pull out another factor of 4 that each of these guys share, and we'd have 40 times the GCD of 176 divided by 4 is 44, and 24 divided by 4 is 6. And we could keep going on like this. You can keep pulling out common factors to then figure out what the GCD of these things is going to be. That may save you a little bit of time in that first step when you have to figure out what your GCD is. This sample here, actually pretty nice to find out what you get. We talked about the greatest common divisor of two integers a and b. Related to it is the least common multiple of a and b, or as we write it, LCM, open parenthesis, a comma b, close parenthesis. The least common multiple of a and b is the integer, and we call it little m, such that a divides m and b divides m. This is just saying that m is a multiple. M is a multiple. What makes it the least common multiple is property number 2. If C is positive, where A divides C and B divides C, then M has to be less than or equal to C. So this is what says M is the smallest. Such a multiple. And how are the GCD and the LCM related? It's actually kind of a neat little thing, something that you may or may not have heard of in the past. I'm guessing not. Why it is what it is will probably make a bit more sense as we get later on in the course. But for positive integers a and b, the product of a and b is equal to the product of their GCD and their LCM. So if you are given two positive whole numbers, a and b, like you will be given in this course, and you find the GCD, you can then automatically do one small calculation to figure out what the least common multiple is going to be. Again, why that is what it is will be made more clear later on in this course. So I know this was a long video, but it's a semi-confusing process. Perhaps once you do some more work with it, you start to see why we do this particular process in the way that we do. We're going to do this particular process the exact same way in our next section when we talk about linear Diophantine equations and how do we solve them. We are going to throw in one little extra piece at the end, but we are using this same process. So it is very important to have this down and understand how to do it. If you have any questions or comments, be sure to drop them in the comment section below. Otherwise, until the next video, take it easy, guys.